So yeah, chapter 16, it's not too thick. I'm thinking of getting through it in just one setting, so we'll see. As I lecture chapter 16, it's going to feel a little chunky, but that's because I didn't get a chance to make sure my builds are okay. But that's okay. So historically, when I first started teaching this class, this made sense to me to bring this in because I wanted to, in case you're doing your photo project, I wanted you to be able to put a name with that optical phenomenon. I was talking to, this class is also taught in West Burlington, and I was talking to that physics teacher here today, and I'm like, oh, we're doing chapter 16, blah, blah, blah. And he's like, well, I don't even do chapter 16. So, teachers can kind of pick and choose. So, but I mean, what's not to like about a rainbow? So we'll talk about rainbows, but one of the things I want you to notice about rainbows is it's got the red. Remember we talked about Roy G. Biv? Okay, red is the long wavelength, and violet is the shortest wavelength. So the shortest wavelength actually is in the center. And you guys know sometimes there's two rainbows. There's like a double rainbow. Don't really see this one, but it would be out over here if there was a double rainbow. And its colors would go, the secondary rainbow, it would go red, orange, yellow, green, blue, indigo, violet, out that way. So you kind of have the reds in the middle and the violets on that side. I still can remember our daughter being like first grade or something and drawing a rainbow, and she like did it the right, and I'm like, oh my gosh, that is so cool. Okay, so why do rainbows occur in the atmosphere? Actually, why do a lot of optical phenomena occur? They kind of fall under these sort of four things that are going on. And the first two we can pretty much is what I'm going to focus on. The idea of light being reflected and light being refracted. So we'll talk about what that is. But before we get into the nitty-gritty, we talked about this before, that if you have light from the sun, okay, it can interact with particles in the atmosphere, and you have, like, the light can be transmitted, it can be absorbed, or it can be scattered, reflected. So that's kind of what we have going on. So talking about a mirror reflection, so there's this thing called the law of reflection, and actually that made it to your review sheet for your exam. So all the law of reflection means, and you guys we do this all the time, is the angle that the light hits the mirror, okay, is going to be equal to the angle that it leaves. And those two angles that I'm talking about are kind of what we say relative to a line drawn perpendicular or normal to the mirror itself. Okay, so the angle of reflection is equal to the angle of incidence. So reflection. Well, not all surfaces are smooth like that. Okay, like if this was like aluminum foil instead of like a mirror, okay, the aluminum foil kind of has like little dips and dimples and things like that. And so reflection is going to occur, but it's not like an orderly reflection. It's just kind of more like scattering. Okay. So here's a picture of a phenomenon that's happening, and this is reflection. But this is reflection on like a not smooth surface. So basically we have kind of dimples and dips and everything in that water, making that cool image of the sun being reflected off the water. So here's where, and we'll be looking at other optical phenomena like this. Do you guys buy this? That if we are standing here, okay, we are seeing this light directly from the sun, never look at the sun, but we're also seeing the light here as the sun's image came down here and was reflected off. Okay, so that's kind of, we get to see two suns in that sense. And that'll come up when we talk about mirages. So there's this has got to be the cutest picture. This is new to this edition of the textbook. I just think it's adorable. Okay, it's called internal reflection. And the description goes something like, basically you have light, and I'll use the light from the image of this adorable little girl here. Okay, light is coming directly to us, the camera or whatever. Light is also going in all directions. One of the directions is up here. Now we're going to be talking about medium that light travels through. We have two mediums here. We have the water, that's one medium. Okay, and above the water, hopefully these people since they're not mermaids, we have air. Okay, so we have air and water. Okay, so basically light from that young lady is coming towards the camera, and it's also going up to the interface, which is the light and air, and then that image is being reflected back down. So I just think that is so cool. It's called internal reflection. Okay, so that was reflection. There's two R's. Refraction, okay, refraction is bending of light. And the reason light is bent is because refraction occurs as light travels from one medium to another. So the example here is going the two medium, okay, we have we have light that is going from air into water. And I'm not going to get into it, the nitty-gritty of it, I don't think at all, but there's these things called the refractive index of the substance. Diamonds have a different refractive index than water. Okay, and the difference, refractive index is an indication of how fast light will travel in that medium. Okay, so light, as it transitions from air to water, is bent. So can you see the bending right there? Okay, literally, okay. So that actually, if you were a person down here in this water, for instance, down here, it would look like that shaft of light came from, let's see, what color should I choose? I'll choose orange. It will look like that shaft of light came from up here. That's what it will appear where it came from, even though it really came from here, and it was bent. Okay, this is what appears, and this is what it really was, where it really originated from. There's a lot of cool things, a lot of tricks that light can play on us like that. So refraction occurs as light travels from one medium to another. Let's see. Must be on the next slide. Oh, there it is. But why does it bend? And it bends because actually it travels at a different speed in those two mediums. And I've heard it kind of described. It's funny because I think of, sometimes in astronomy we emphasize what's the speed of light. You know, it's like 186,000 kilometers per second. Okay, the speed of light. The speed of light doesn't change. Well, that's the speed of light in a vacuum. Okay, if you go ahead and introduce a medium, it can travel different speeds. It does travel different speeds. It'll always be slower than the speed of light in a vacuum. So if it travels more slowly, we can kind of think of it in this sort of kind of analogy. So you guys would probably tell me, I'll put this whole thing up here. You guys would probably tell me that on this slick, we'll be talking more about that in chapter 6, okay, but on something that's slick, there's no friction, so it's probably moving faster, okay? So what happens then when it goes from something slick to something bumpy is it's going to slow. It's going to slow down, just like light going from air to water will slow down. As it does that, it basically, the part of, because light is a wave, the part of the wave, the part of the light that hits the interface first is going to be actually swung around. This part is going to keep going fast momentarily upon impact. Well, kind of think of it as a kind of, this hits first, and then this swings around, and voila, it has changed its trajectory. Okay, so that's always what it's going to be. And I think this thing up here kind of says the scary thing, like if you fall asleep at the wheel and you go from your nice smooth pavement onto gravel, of course your car is going to respond, going to slow down on the gravel as it was to the pavement, and so your right wheel is going to slow down and your left wheel is going to keep going fast. And that's why just momentarily you're going to change your trajectory. Then you'll all be on gravel, then grass or whatever. Okay, so it's that same sort of phenomenon. That's refraction, changing medium. This is refraction too. You kind of have to look closely. Okay, so there's a photo up here, okay, and then the figure down here showing you the exact same thing. So it's a subtle thing, but if you look at the photo, it seems, the pencil seems to kind of do a bend right here. Oops, let me choose a different color. Oops. let me choose green. It kind of goes, kind of has a kink right there, right where, okay. So the deal is the reason we see that pencil is because light is entering our eyes from that pencil. Light probably came from the room, from a lamp or whatever. So light from a lamp hits the pencil. Remember, it's that color that's not absorbed, that comes back, goes in all directions, including ours. So in the case of the here, okay, there's no extra medium for that light to travel to get to us. In the case of here, basically, you have the pencil illuminated, but it has to go from the water back through air back to us. So it makes it look bent. The light is refracted. That's kind of being shown here in a different orientation. Okay. The part of the pencil that's down under the water, the light from the pencil is actually refracted as it comes out to us. This is not refracted. All right. So refraction, a lot of stuff goes on with refraction. This might, I don't know if it'll make you feel better or worse at about nighttime, but refraction occurs as light travels through different medium. And remember, one of the things that you guys already knew before you took this class is that the air at the Earth's surface is very dense. I'll go ahead and put lots of little dots there. And the air at upper elevations is pretty sparse. So I'll just kind of put a few dots there. Okay. I have just described two different medium. And granted, basically it's kind of a gradual sort of thickening of the air, increasing density of the air. But we have low density here, high density here, and that actually causes refraction to occur. So here's what that means on a practical sense. The sun can be relatively low, okay, but the sun will appear to be higher than it really is. That's because the sun's light is refracted. Yeah. We're going to talk about something called a green flash coming up, which is kind of fun. Basically, and I've never seen one, I guess it's on my bucket list. Basically, as the sun sets, okay, kind of this whole refraction process, the last tippy top color to go down is going to be green. And so actually, I've got a picture of it. You can see kind of little, it's in your textbook too, a little bit of green because of this refraction.
So it's kind of like a Pirates of the Caribbean movie?
Yeah, I think so, probably. Yeah. Did they show the
like they
green
flip the
flash?
ship over and then how they come back is they explain it and then there'll be like a flat green flash.
Could be. Yeah. I like that.
That's the second one.
Is there three now?
Third one.
And is that the most recent one?
No, there's a fourth one.
Okay. I'm kind of behind. I'll have to check it out. But yeah, that's exactly, because I double checked, it can happen at sunrise too, sunrise and sunset. So refraction. Very good. Okay. So you've probably all seen mirages. The one we are probably most familiar with is the one, and I have a picture of it coming up, the one where you're driving down the road and it looks like there's a puddle of water in the road. That's a mirage. Okay? That's an example of, actually there's two types of mirages. That's an inferior mirage. And mirages are created, both types of mirages. This one's an inferior mirage, and the other one's a superior mirage. Both types of mirages are created because of differences not in density, but temperature. Oh my gosh, you guys have seen this before where there's like a flame, a candle that's lit, okay? And have you ever like looked beyond it and it looks like kind of waves like that, okay? So what's happening is that candle is heating the air right in the vicinity of the flame. So we have hot air and we have cold air. And then sometimes kind of the flame can kind of ebb and flow, so it gets hot and cold and hot and cold. So we can have blobs of hot and blobs of cold air. Well, those both have different, what we call refractive indexes. Those both have, hot and cold air are different mediums, okay? So as the light travels through those different mediums, then the light is refracted. So what's happening is the object that you're looking at back here, basically it looks like it's kind of moving because the light from that image is being bent as you have different blobs of temperatures of air going between you and the object you're looking at. This is actually the same reason why stars twinkle. So on a larger scale, in the atmosphere, the stars out there, here's the atmosphere, and basically we kind of have blobs of cool and warm air kind of alternating going between us and the star. So that's refraction. Now, an inferior mirage is caused by refraction. I'm going to try to convince you of this, but inferior, if you think inferior, think down, doesn't mean it's bad. It just means the mirage that you see while you're driving down the road, I'm going to try to convince you, basically, if this is the road right here, what you're seeing is basically trees that are, or sky or whatever, in the road. So it's an inferior mirage. It's below the horizon, okay? And it will be inverted. Now, you may not be able to kind of make out the trees or whatever, but if you were to be able to look at it, if this is my tree standing up, okay, my tree down here would be like this. It'd be upside down. So below the horizon, upside down. And we have the temperature thing going on. Those are most likely to occur when the sun's been shining and your asphalt is nice and toasty. So the temperature thing we have going on is we have really hot and then just normal cooling off. So really hot and cooler air is what's creating those inferior mirages. So we have the classic, the guy out in the desert, okay, looking for some shade. So this is where, remember I said you see the sun twice, okay? So this guy sees this palm tree, okay? Light from the sun is reflecting off of the palm tree, and he sees a normal palm tree. But also, light from light from this palm tree is going in all directions. One of the directions is down here. Okay, instead of just kind of going down here so his feet could see it, actually that air is bent, okay, because it's refracted. And it kind of gets, instead of going a down trajectory, it gets a going up trajectory. So this tail end right here, that light that is bent up, refracted back to him, creates this image that he sees down here. So he sees two palm trees. And notice the one that he sees below the horizon, that's a mirage, and it's upside down. So I don't really see that. But here, this is a good example of, you can kind of see where this is all kind of like glassy. Okay, that's a mirage created by the same reason, nice hot air, what we call a steep temperature change, a steep temperature gradient. And you can probably kind of see the car. I can't tell that it's upside down, but I'll have to take their word for it. Yeah. So that's an inferior mirage, and it's the one that I've never seen the other one. This is a superior mirage coming up, so I'll put this whole slide up here. Inferior mirage, superior mirage. They're both due to refraction, but at superior mirage, think super, think like above, and actually these are going to be images that float above the horizon. These would be creepy, I think. I'm going to show you a figure and then a photo of a superior mirage. So what's happening here is we have a temperature inversion in place. Now remember what a temperature inversion is. We've talked about those before. I'll draw just a little temperature inversion up here. So that's my surface of the Earth. Okay, usually the temperatures as you go up, we know, get from the troposphere, they get cooler, usually cooler as you go up. So that means that we have the hottest temperature here, okay, usually. So for a temperature inversion, though, what we've got is we have relatively chilly, cold air here, okay, and we've got warmer air here, and then we've got colder air above there. Okay, so actually I would say beginning about here, okay, then we have a normal profile. Okay, this is normal. That's not the temperature inversion. The temperature inversion is we have cold air right there. So superior mirage is created because of a temperature inversion in place like that. And here we go. Personally, I would not like to see a ship where it's supposed to be and a ship hovering, quite frankly. Like, but it has to do with temperature inversion in place, okay, and that allows for the light to be refracted. So you see the normal one, and you also see an image of it up here. I don't know. But it hovers above the horizon, and it's right side up, not upside down. Now, I tried to find what I thought was a good picture on the internet for superior mirages, and I thought that this one looked like a pretty good one. I can't remember where I got it from. But my thing about this one is, to me, it looks like, and these are mountains in the distance, see what you guys think, but to me it looks like these are upside down. You know, they're not right side up, so I don't know. Anyway, superior mirage, also created by air refracting due to temperatures and differences in temperatures. So the refractions I've been describing, basically the entire packet of light is refracted, all bent the same. Okay, that's to say if something is red, it appears red after the light is refracted. Okay, if something is blue, it appears blue after the light is refracted. Refraction also is the same thing that can separate light into its components. And actually, a long time ago, Newton found this, that if you have a piece of glass that is in special shape of a prism, you can take white light, white visible light, and you can separate it out into what we call its components. You know, so white light, I think we've talked about this before. Like if you turn on a light in here, it's shining Roy G. Biv, okay? And so what a prism does is to separate it. The way a prism works to separate it is that, and I think it says it on this slide, that actually red color, this red right here, is bent the least, okay? And violet is bent the most. When we get to green flashes, that actually is a player. So Rayleigh scattering, you know, the skies are blue. Basically, our blue indigo violet is all filtered out. So actually, that's why the last color to set is actually green for us to see. That's what causes the green flash. Okay. So refraction is not only just bending of light to keep its same color, but also it's bending of light and breaking it out by its wavelength. Okay, that's also refraction. And we're going to see actually for rainbows to do their thing, we got to have this sort of refraction going on. Bending of light and selective to wavelength and breaking out into its components. So here's the green flash. The flash, that's a good show. I think my husband, he didn't binge watch, but I think he finished all the flashes he can watch for now. But that is a setting or rising sun. And actually, if you want to at the top there, because I double checked this, because I'm like, really? Setting or rising sun. Okay. And it's on my bucket list. But like this says, you need to have a nice unobscured view of the horizon, which isn't too bad. But you also want it to have nice, the atmosphere needs to be pretty darn clear, because you're trying to be really picky and get that green light to you. So I think that's cool. All right, what else we got? Okay, on to rainbows. So yeah, rainbows, you're always going to see the red on the outside and the violet on the inside. So I'm going to draw a little picture of what this is describing. Basically, if this is my horizon, okay, and this is my little person right here who wants to see the rainbow, you need to have the sun relatively low. Put the sun over here at sunrise or sunset, probably usually sunset, more likely. And then, so that's got to have the back be to the observer's back. And then over here, you need to have basically kind of some still liquid water droplets that are suspended here. So this is liquid cloud droplets. And so I'm going to show you a figure from your textbook, and it's going to show you how basically the light comes from the sun, it interacts with your rain droplets, and then it creates a rainbow. That's it. Kind of picky. Okay. So you'll always see the rainbow will be on the opposite horizon of the sun. The rainbows we've looked at are the primary rainbows. It'll be the darker one. If there is another one, it'll be called a secondary rainbow, and it's outside. It'll be a little dimmer. I love rainbow photos. And like I said before, the primary rainbow is going to have the violet on the inside, and the red is going to be on the outside. And if there is a secondary one, the secondary one kind of picks up with red where the primary one left off. That works. All right, so let's take a look at, well, I guess there's a figure coming up. These three kind of bullets go with the figure on the next slide, so it's kind of easier to show you. But kind of summing it up, what you're going to read here and see on the figure on the next slide is a rainbow is equal to refraction. Oops. Really? Refraction, that's the bending of light, plus reflection. Actually, it's what we call internal reflection. All right, here's what it looks like. Okay, now this has got to be one of the scarier figures in this textbook. Check this out. I hope this is not drawn to scale. There's that little tiny person down there, and here is this liquid water droplet. You're like, oh my gosh. Okay, but I like this figure aside from it being not drawn to scale. Okay, so the sun's rays enter the little liquid water droplets, because remember I kind of showed the cloud, and you have to have liquid water droplets suspended there. Okay, so it enters, okay, it is, you can kind of see this refracting, okay, and actually with this refracting we have separation. It's refracting, separating at the same time. It's like a prism. Now the refraction is occurring because we have air and water. Okay, and then remember that cute little girl who actually we could see an image of her inside the pool bouncing off kind of the interface between the liquid water and that's exactly what's happening at the back of the water droplet. Is that not cool or what? So this is reflection. And so actually we see it reflecting, and the red, the different colors, the colors are already separated. So when they reflect off, they just kind of continue on their own little trajectory. Then we have one more refraction. Okay, of course, why do we have that last refraction? Because it's going from liquid to air now. Okay, so it has this kind of characteristic refraction, reflection, refraction. That is so cool. I just think that's neat. Okay. So, what about a secondary rainbow? Well, here's a pretty picture of one. Over here. So you can see the secondary rainbow on the outside of the primary rainbow, and you can kind of see where the reds kind of match up, and it picks up, so the violets on the outside there. Now, for that to happen, we need to have an extra, let's see what it is, an extra internal reflection. Okay, So let's see. Oh, sun's rays are showing entering here. Okay, we have refraction here, separating into its colors. We have internal reflection, and then refraction here as it leaves. I think that's gold. All right. So we kind of end up now talking about some other kind of pretty things you see in the sky other than rainbows. And one of the things you probably want to focus on for your homework and for your test is to kind of get a sense for what these are, what they look like, and what's causing them. So a halo, I'm going to show you a picture here in a minute, but a halo is like an angel's halo. So in the middle of the halo will either be the sun or the moon. Okay, so that's what a halo is. And halos are caused by the presence of ice crystals. Okay, let's see, they can be around the sun or the moon. Let's see. And remember, we talked about cloud types in this unit. We said the cirrostratus or the cirrus clouds, those are both upper level clouds, and that makes sense, they'd be ice crystals. Okay. So these are pictures of halos. The top one, the upper left hand corner, over here, this is the sun in the center here. This is the moon in the center here. Kind of wispy looking things. Halos to me, though, instead of the other thing I'm going to show you just momentarily called a corona, with a halo I see a little bit of color. It seems like I see more color with a halo than I do coronas. Sundogs can be kind of related a little bit to halos. But sundogs, there's either one or a pair of them. So sundog or sundogs. Okay, that's what I call them. I don't call them that parhelia. Let's see, what else do we have? We need ice crystals. So if you asked how they're formed by the presence of ice crystals in the cirrostratus or cirrus clouds. The other thing, though, unlike halos, is that the sun, and you don't see sundogs around the moon. I've never seen one anyway. See sundogs around the sun, either one or two, like this will be the sun, and you'll see them here, like a pair or one. And the sun needs to be low on the horizon. So actually in the morning, a lot of times, if we have those wispy clouds up on my way to work, I'll see one or two of them. So let's see. And sometimes they definitely have a color to them. And so sometimes actually they'll look kind of like a little mini rainbow, kind of spread out on either side of the sun. So here they are. Here's a picture. So the blobby thing in the center, this is not the best picture of sundogs that I've ever seen, but the blobby thing in the middle is the sun, and then we have a pair of sundogs on either side. Not bad. Kind of pretty. There's another phenomenon called a sun pillar, and if anybody asks you, they are also caused by ice crystals, so all of these are ice crystals to start out with. The sun must also be low on the horizon. And as the name applies, basically it looks like kind of a pillar. It can go up or down from the sun. And they look like this. So this is just a sun pillar up. It's pretty. All right. Glory. So you may not have seen glory before. Glory now, we have a different, it's not ice crystals, but if you read down here at the bottom, it's actually suspended mist, suspended liquid particles. And your textbook says that if you're riding in an airplane, there's a possibility you can actually see a glory out the window, kind of in the cloud. I've never seen one. But I swear sometimes I'll be at Walmart shopping in the parking lot. It's kind of like, there's like drizzle. And actually this is mostly at nighttime, I'd say, and you can kind of see a visual effect around the lights in the parking lot. So I don't know. But those are glory. And again, they have color associated with them. Okay. So now we're on to corona. Corona are also liquid particles. Okay. So these would be mid-level clouds because it's still liquid. And so if it's mid-level flat clouds, mid-level would be alto, flat would be stratus. So alto stratus clouds. Now these things, you can tell it's not a halo because they actually touch either the moon or the sun. So there's not any space between it. And this says it can have a bit of color too. So they look like this. I would say that the moon, I mean, you can just barely kind of see. I don't know. And this one almost looks like a halo instead of a corona. Not the best pictures of what I think of a corona, but that's okay. Hopefully you got the right idea. But it's liquid particles, not ice particles. And so here's the last slide. And if any of you guys stick around for the review session, I'm going to pull this one up again. Because like I said, you want to especially pay attention to the optical phenomenon, kind of what it looks like, but also what's causing it. Is it ice crystals? Let's see, is it rain droplets, like a rainbow? Or is it liquid water particles, like the glory and the corona? Okay. So let's go ahead and take our break early, if that's okay with you. And then we'll come back and do a little bit of Chapter 6, but won't get to the end.